Hello students, this is lesson U4A07A. By the end of the lesson, you should be able to say, I can use properties of sides, angles, and diagonals to identify a kite. So let's just recap. This is actually going to be the last quadrilateral that we are going to study in the lesson series. So for since the beginning of this unit, we talked about polygons, and then in the second lesson we talked about quadrilaterals, and more specifically, we talked about parallelograms. Then following parallelograms, we talked about rectangles. Following rectangles, rhombuses, and squares. And in the last lesson, we talked about trapezoids. In this lesson, we are going to be talking about kites. So what exactly makes a quadrilateral a kite? So a very traditional looking kite, because a kite can take many different forms. A kite is simply a shape that looks like this. Now, how do you describe that, right? So a more technical way of describing it is it's a quadrilateral with two pairs of adjacent congruent sides. And the key word here is the sides, they have to be two adjacent pairs of congruent sides. So notice in this diagram over here, segment AB is congruent to segment BC. Segment AD is congruent to segment CD. Okay? Those are adjacent pairs of sides that are congruent to one another. With that restriction in place, okay, comes another property. So if I take a look at this and construct a line right down the middle, okay, forming diagonals, we can then see that that one diagonal is actually going to end up being the perpendicular bisector of the other. And if you need convincing as to why this is the case, I encourage you to pause the video and to convince yourself why this is the case. I'm not going to do this in this video just because I want to get through some of the key concepts related to some of the algebra that's involved, okay? But the main takeaway is one diagonal will be the perpendicular bisector of the other. They are not perpendicular bisectors of each other, unlike a rhombus or a square, okay? So that's the main difference here. So you can actually think of a rhombus as being a kite because there's nothing to suggest that you can't have that diagonals be perpendicular bisectors of each other, okay? As long as there's only one, right? And the same thing could be said about the two pairs of adjacent congruent sides. Nothing there is saying that they can't all have congruent sides. All right. So let's take a look at our first example here. You're told that ABCD is a kite. What you need to do is find the side lengths of BC, DC, AB, AD. If you know these segments, BC is equal to 5x plus 4, DC is equal to 6x, and AB is equal to 2x plus 1. I encourage you to pause the video and try to solve this problem on your own. So hopefully you had some time to figure this out, and recognizing that this is in fact a kite, immediately I noticed that there are going to be two pairs of congruent right triangles involved here. BC is 5x plus 4. That is actually the hypotenuse of one of the two types of right triangles I see. Same thing with DC. DC is also a hypotenuse. But I also recognize that BC and DC are going to end up being the same things. They are going to be congruent to one another. So a good place to start is to actually find out what BC and DC is by equating them with one another. So since BC is equal to DC, I can say that 5x plus 4 will equal to 6x. Or in other words, x will equal to 4. So since x is equal to 4, I know that BC and DC, as well as AB, can be found pretty easily. I know that BC will equal to 24, DC will also equal to 24, AB will equal to 9. Since AB is equal to 9, I also know that AD will also equal to 9 because I'm dealing with a kite. Those two adjacent pairs of sides should be the same length. Alright, so let's try, please pause the video, see if you can figure this out on your own. So hopefully you guys had some time to think about this. So PQRS is a kite. We need to find that the side lengths of QT, TS, PQ, and PS. So again, looking at this, I know that PR and QT, well, I'm given the length of PR, I'm given the length of QT is given by that expression there, and then TS is given by 5n minus 8, and then finally QT, once again, I'm told that QT is equal to 11. So wait a second here. I'm given actually two things. I'm given the expression. I'm also given the a numerical value here. I know that PT is equal to TR. So therefore PT must be half of PR, which is going to be 3. Okay. So if PT is 3, or TR is equal to 3, I also immediately recognize that QT plus TS is equal to QS. And I'm told the lengths of some of these segments here. I'm told that 10 minus 2n plus 5n minus 8 will equal to 11. So I actually made a mistake here. This should say QS, not QT. My apologies. So those segments, okay, QT plus TS is equal to QS. If I combine like terms, I will end up with 3n plus 2 is equal to 11. Subtract both sides by 2, divide by 3, I will end up with n is equal to 3. So since n is equal to 3, I can then go back and I can figure out what is QT and TS. QT will end up being 4, and TS will end up being 7. And since I'm dealing with right triangles here, I can then figure out the side lengths of PQ. Since PQ is a hypotenuse, and I know the length of QT, and I know the length of PT, the length of QT is 4. The length of PT, well, the length of PT, isn't that just 3? We found that earlier. So therefore, this is a Pythagorean triple. So therefore, PQ is equal to 5. And lastly, I can do the same thing to find out what is the length of PS. So I know that PT is 3, TS is equal to 7. I can then, again, apply the Pythagorean theorem. I know that PS, therefore, is equal to square root of 58, or actually, that's it. You cannot reduce square root of 58. So that's it. PS is equal to square root of 58.